In this video, we're going to start talking about heat pumps a little. For those who have a modern refrigeration book, this goes along with chapter 40 in your book in the 20th edition. So what we want to accomplish here is we want to describe the basic of a operation of a heat pump in a heating mode and in a cooling mode. We want to summarize the difference between ground source heat pumps and air source heat pumps. We want to identify heat pumps' principal components. We want to explain how a reversing valve operates and controls the direction of refrigerant flow through a heat pump. We want to compare and contrast different types of coils and loops used in heat pump systems. We want to be able to list two common methods used to defrost heat pumps. We want to understand how auxiliary heat is used in conjunction with heat pumps. We want to summarize how heat pumps can be combined with solar heating. And we want to be able to perform routine maintenance and service on heat pump systems. So let's talk about overall heat pump operation first. Heat pumps use a compression refrigeration system, just like air conditioning does. We add a component called a reversing valve that allows both heating and cooling to occur. Heat always moves from warmer substances to cooler substances. Coil cooler than the surrounding air absorbs heat. Coils warmer than the surrounding air releases heat. Think about this in a standard air conditioning system. The evaporator is inside, okay, and it's cooler than the air blowing across it. We might have a 36-degree evaporator and 76-degree air blowing across it. The cooler coil absorbs the heat. Then we use a compressor to increase the pressure and temperature of that refrigerant, and we put it into the condenser coil, which is warmer than the surrounding area, so that it releases heat. Okay, two very important concepts. I don't care where these coils are, but a coil cooler than the surrounding air absorbs heat. A coil warmer than the surrounding air releases heat. There's two heat exchangers that switch function depending on the mode. So we do not have, when we talk about heat pumps, we do not use the term condenser and evaporator. We use the terms indoor coil and outdoor coil. They switch functions depending on modes. So if we are in a heating mode, my indoor coil is warmer than the surrounding air and is releasing heat, and it performs the function of a condenser. The outdoor coil is the evaporator, which is cooler than the surrounding air, and it absorbs heat, and it becomes the evaporator. We have a reversing valve, that is the valve that actually reverses the functionality of the indoor coil and the outdoor coil. So when we go into cooling mode, the reversing valve switches position. And if you take a look at the internal of the valve here, you will see that all of a sudden our discharge line and our suction line has switched positions. Okay, so my reversing valve in a heating mode, the gas discharges out of the compressor, goes through the reversing valve, and goes to the indoor coil where it gives up heat to the surrounding air. In cooling mode, my discharge through the reversing valve, which is slid over, okay, my discharge from my compressor goes through the reversing valve into the outdoor coil. The key concept is the compressor never changes direction. It's not like we change the direction of the compressor. We just reroute the suction line and the discharge line. So when I take my pressures here, okay, on the discharge and suction line, regardless of the position that the reversing valve is, I am getting a true suction and a discharge pressures. So again, the reversing valve is the heart of the controls of a heat pump system. The air source heat pump uses outdoor air as a heat source or heat sink. The performance and efficiency is based 100% on the outdoor air temperature. Air-to-air heat pumps are extremely frequent as split systems and package systems. The other type of heat pump is an air-to-water heat pump. We also use ground source heat pumps. It uses the Earth's thermal energy as a heat source or heat sink. It could also be called geothermal. It minimizes temperature variations because the temperature underground and underwater remain fairly constant. This system can be designed for greater efficiency. It can be a direct exchange, in other words, the refrigerant loop is buried, or it could be a water source using a water loop. A direct exchange heat pump circulates only refrigerant. There's no water involved. The outdoor coil is directly in contact with the earth. Okay, in other words, we actually bury refrigerant tubing underground in the outdoor. So the components of this system is a sealed underground outdoor coil. We have an indoor coil, we have a compressor, we have a reversing valve, and a metering device. The water source heat pump circulates water through the ground loop or underground or underwater. Water acts as a heat transfer media. The heat transfer between the water and the refrigerant occurs in a water coil, heat exchanger. Okay, so this is a picture of the internal components of a water to air system. Okay, we have a compressor, okay, and we have a reversing valve in here, and we have a coil. Okay, it's a water to refrigerant heat exchange. Okay, in the heating mode, okay, we circulate the cooler refrigerant where it would be the evaporator. Okay, we put it through a water coil. We pull our suction gas back to the compressor. Okay, the water coil is connected to ground or water loop that's circulating water. It's absorbing heat from the warmer outdoor ground. Okay, the indoor coil gives up heat to the air that's blowing across it, which is cooler. In the cooling mode, I'm rejecting heat from that coil, which is now my condenser, and I'm pushing it into I'm giving it up to the water or ground loop. We have open and closed loop systems. Open loop heat pump systems uses well or lakes as water sources. Water surface sources serves as both supply and discharge. They require a large amount of clean water, and in many municipalities where water is measured and metered, these are no longer allowed. Okay, open loop systems have some restrictions on installation because of water conservation efforts. Closed loop heat pump systems circulate the same water or refrigerant. Okay, again, open loop system is over here on the right. It uses a pump or well to pump water, and then it rejects it back into someplace outside where the water can go safely. Closed loop systems either circulate the refrigerant directly or they use water loops. Okay. Heat pump efficiencies use a variety of methods for gauging the efficiencies. Okay, they can use energy efficiency ratio, which is EER, seasonal energy efficiency ratio, which is SEER, heating seasonal performance factor, which is HSPF, and they can use coefficient of performance. Air source heat pumps for split systems can actually hit up to 14.5 SEER, 12 EER, or 8.2 HSPF. Packaged units are a little bit lower. Ground source heat pumps, they can hit up to 17.1 or 21.1. Okay, again, open loop isn't allowed in a lot of locations anymore. So we're basically talking, we're going to do like 17.1. Coefficient of performance, 3.6, 4.1. Again, open loop really is not allowed anymore in a lot of locations. Heat pump components. Okay, this is a package unit. Okay, you see these outside commercial buildings. You can see them outside mobile homes a lot of times. Okay, you have an outdoor fan, you have an indoor coil, you have an outdoor coil, you have a reversing valve, you have a compressor. We usually see an accumulator to prevent liquid refrigerant from hitting the compressor. We have a metering device, sometimes two metering devices, one on the indoor coil, one on the outdoor coil. The reason for the accumulant is that heat pumps require more refrigerant in the cooling mode than in the heating mode. Accumulators also store excess refrigerant during heating. A charge compensator tank may replace an accumulator in some systems, rarely. What the accumulator does, it allows liquid refrigerant to sit without getting into the compressor. The compressors in heat pump systems operate at lower ambient temperatures than air conditioning compressors. They're designed to handle a little bit of liquid slugging. Most of them will be scroll compressors now. They have slow startup routines, they have stronger valves, and the accumulators they have two-way filter dryers. If you ever replace a filter dryer at a heat pump system, make sure it's called a bidirectional or two-way filter dryer. They will usually have crankcase heaters installed. So if you look here, you'll see a little band around the bottom of the compressor. That's a crankcase heater. The metering device is needed at each heat exchanger. Most often the types used are Fixed-Orifice, capillary tubes, TXV, or flow check pistons. You're going to see TXVs as the primary in newer systems. Older systems will have Fixed-Orifice. Rarely you'll see capillary tubes unless it's a PTAC unit or a window unit. Fixed orifice metering devices and capillary tubes, they cannot meter flow based on evaporator outlet temperature. In other words, they cannot tell what that superheat is. They have to be sized for a specific flow amount, and there's different sizes used for the indoor and outdoor coils. TXVs, thermostatic expansion valves, they generally allow flow in only one direction. Okay? If you have issues with the TXV, check the valves running parallel to each TXV. And you can have biflow TXVs. They must have MOP compatible with coil and compressors. So if we look at the diagram here, we will see how this works. This system is in the cooling mode. So we're sending our discharge gas from the compressor through our outdoor coil. It is not going through the TXV. It is going through the check valve. It is then going to the liquid line, and since the check valve is blocking the flow because the check valve only allows flow the other direction, it goes through the TXV to the indoor coil, which is acting as the evaporator, and it goes back through the system. If this were reversed, okay, the flow would be reversed. This check valve would close, forcing the refrigerant through the TXV on the outdoor coil, thus making it the evaporator. Okay, the indoor coil, this would be, the check valve would be open and the TXV would not be in play. The indoor coil would become, okay, the indoor coil would become the condenser. Flow check pistons meters refrigerant flow in one direction. It allows the refrigerant to flow freely and unrestricted in the other direction. Systems use two flow check pistons orientated in opposite directions. So if you ever have to replace one of these, make sure it's put in the correct direction. They will have arrows on them. A reversing valve, we've talked about it a number of times so far, but a reversing valve reverses the flow of refrigerant to the indoor and outdoor coils. For cooling, refrigerant is routed from indoor coil to the compressor, from the compressor to the outdoor coil. Okay? For heating, refrigerant is routed from the outdoor coil to the compressor and from the compressor to the indoor coil. Now be very careful about this because sometimes de-energized is no longer cooling. Okay, so make very sure you understand when you're connecting the wires. Is it energized for cooling or de-energized for cooling? Most often, if you have an O terminal, okay, an O terminal on the condensing unit or on the outdoor unit, it means that it's energized for cooling. The de-energized position is heating. Okay, so just always be aware that if the reversing valve is energized, is it cooling or heating? If you start a system up and if you have your thermostat set for cooling and the condenser or the outdoor unit is blowing cold air, it means that you have to change the position of that reversing valve wire. You have two types of reversing valves. You have a direct acting reversing valve that uses a direct action of a solenoid plunger, does not require a pilot tube. You also have a pilot operating valve. It uses a solenoid pilot valve and it's needed in larger heat pumps. Okay? If you look at the reversing valve and you see a solenoid and then you see little capillary tubes running across it like in this picture, okay, it is a pilot operated reversing valve. It is very rare these days to see a direct acting reversing valve. So what happens here is because of the refrigerant pressures, the 24 volt operated solenoid does not have enough power to overcome the high refrigerant pressure. So what we do is we open and close a pilot valve, okay, which sort of mirrors the reversing valve to allow the high pressure refrigerant to flow on either side of this main piston. Okay, so this is a de-energized pilot valve. Okay, so we're allowing refrigerant to flow out of the compressor discharge through the pilot valve and into the right side of the cylinder, which pushes the piston over, okay, and pushes it into cooling mode. Then we energize the pilot valve solenoid, okay, which pulls that piston over into the solenoid. Okay, we now allow our discharge gas to come through the capillary tubes on the left side of the piston and it pushes it into heating mode. And again, de-energized and energized for heating or cooling will vary on different units. Always make sure you've checked that. Okay, and most often it's going to be an O or a B terminal. Okay, if it's a B terminal, most often it's energized for the cooling or for the heating mode. If it's an O terminal, most often it's energized for the cooling mode. We usually want systems to fail into heating mode. Okay, coils and loops. There's two terms here. Okay, a coil is tubing carrying refrigerant. Air coil and water coil. But a coil is tubing carrying refrigerant. And all we're saying is air blowing across it, or are we exchanging heat to water? A loop is tubing or piping carrying water or a water-based solution. Could be a ground loop, could be a water loop. All those two terms say, is it in the ground or is it in the water? Air coils circulate refrigerant and absorb heat from or release heat to the air. The fins are on the coils to increase heat exchange surface area. The larger the surface area, the more heat is going to be exchanged. The fans pull air through the coils, We don't push air through the coils. If a fan is running backwards, air is coming out of the side of the coils. If the fan is running in the correct direction, we are pulling air through the coils. Ground coils is underground tubing which refrigerant is circulated in a ground source heat pump. The outdoor coil is direct exchange for the heat pump. In other words, we, out of our compressor or out of our heat pump outdoor cabinet, we actually go to a distributor that's buried underground and circulates refrigerant through ground coils. Okay, it's very difficult to repair or troubleshoot. You cannot find leaks easily in these coils. Okay, and when you put copper or brass, usually copper, in contact with the ground, you have electrolytic action that occurs and it will start to corrode. These coils that are buried in direct contact with the ground do not have a high lifespan. Additionally, you have to know exactly where these coils are, and when houses change ownerships, sometimes people build new things on the property and can actually break these coils. Water coils, heat transfers between the refrigerant from an indoor coil and water from the water loop. It's installed near the indoor coil. Refrigerant and water are pumped in separate but adjacent tubes. Sometimes one tube might be inside each other. Okay, it's a water to refrigerant heat exchange. Now, water loops are tubing running to and from the water coil. Tubing can be submerged in a body of water. It's used in closed-loop water-based systems. The tubing water does not mix with the body of water or refrigerant. It's a separate loop. Common water-based solutions. This is the water that's inside the water loops. You could have calcium chloride, sodium chloride, that's salt-based. You can use propylene glycol or ethylene glycol, that's glycol-based. And you can use alcohols, which is methyl alcohol, ethyl alcohol, and isopropyl alcohol. Okay, all of these are solutions that can be put inside the water loops to prevent them from freezing and encourage better heat exchange. You have to look at manufacturer recommendations for both the system and the material that the water loop is based on to figure out which is the correct one to use. There's also some environmental reasons why you can't use some of these in certain areas. Ground loops is tubing running from the water coil underground. It transfers heat between the water coil and the ground. It can be horizontal or vertical. It can run in series or with parallel branches. So if we look over here, vertical ground loops, they're deep. Okay, they come out of the house. Okay, some are vertical, some are in series, and some use a manifold where each one is individual. Okay. You can have horizontal ground loops, which use large surface area of ground. Okay, widespread ground loop, either in series or parallel. Both arrangements have pluses and minuses. Okay, the vertical loops, you have to have someone drill wells. The series arrangement or the horizontal loops, you basically take a bulldozer, bulldoze down, put it in, and then backfill the dirt over it. Temperature controls, okay, in heat pump systems are relatively easy. The thermostat function turns the system on and off, selects a heating or cooling mode, selects fan operations, and can initiate auxiliary heat. Thermostats vary by manufacturers. Always read the directions. When replacing a thermostat, don't trust the wire colors. Label each wire with the letter of the terminal. Okay? Heat pumps have a number of additional wires that you don't see in straight air conditioning. Wire according to each wire terminal's identification letters. Always look at a thermostat literature such as wiring or terminal designations because the wiring may vary. Defrost is important. Okay, the outdoor coil can sometimes be running below freezing. If it's running below freezing because of low outdoor temperatures, frost will start to build up on the coil. You want to make sure that the system melts that ice off of that outdoor coil. That's why we go into defrost. Time and temperature initiated defrost is based on the temperature difference between the outdoor coil and ambient air. Demand defrost runs only when necessary. In other words, it senses if there's ice on the coil. Okay, what it does, you have two options for how we defrost. We can either reverse the cycle. Okay, we can make that outdoor coil warm for a period of time, or we can initiate electric heat defrost. You don't often see the electric heat defrost anymore on heat pumps. Most of the time what we do is we reverse the cycle. In other words, if we're in cooling mode, we shut down the outdoor fan and we put that system into cooling mode to get that outdoor coil warm. At the same time, we have to bring on auxiliary heat inside to make sure that the occupants of the building do not feel that cold air. So every heat pump has auxiliary heat. It's building code. So when the heat pump output equals the heat loss of the conditioned space, we have to bring on auxiliary heat. That's our balance point. If the heat loss is greater than heat production, auxiliary heat is required. Auxiliary heat is a supplemental heat source. In heat pumps, it's usually an electric resistance heating coil, but sometimes in the different parts of the country, it'd be a gas-fired or oil-fired heating system. It's also used during reverse cycle defrost and for emergency heat operation. Sometimes heat pumps can be tied into solar heating systems. Okay, so what we can do sometimes is we can actually use a solar panel to heat some brine solution, and we can use a heat storage tank such as a hot water heater type storage tank. We can put a hydronic coil on top of the system, and we can, when we need auxiliary heat, we can start circulating that heat storage tank solution through the hydronic coil. That can also be used as auxiliary heat in the defrost cycle, because again, remember, when we use reverse cycle defrost, we're all of a sudden making that indoor coil cold, and we're making the outdoor unit the warm coil. So people can feel a cold draft when a system is in defrost. That's why auxiliary heat is required. Heat pump installation is actually pretty critical. Now, this varies a little bit based on the part of the country you're in. This picture is more for the northern part of the country where there could be snow accumulation. In the southern part of the country, you would never see the heat pump on risers. As a matter of fact, it's not legal in the state of Florida. The unit must be level. Electrical service, you have to have the correct voltage and phase, correct wire sizing. In colder climates, you need to install above the total snow height. Okay, you want to make sure the owner knows to shovel snow away from the outdoor unit. We don't want this buried in a snowbank. Now, in the warmer climates, especially in the south, along the Gulf Coast and along the oceans and along the beaches in the south, you have to worry about wind. Okay, we do not want it installed on risers. You want to install it flat on a heavy concrete pad, and you want to make sure it's tied down to the concrete pad. This is called wind protection. Okay, with hurricane force winds, these units will move and flip over. So what you normally do in the southern climates, especially in hurricane areas, you take an angle iron, you attach an angle iron to the base of the unit and an angle iron to the concrete pad it sits on. Or you pull the cover off and you bolt through the bottom of the pad and through the bottom of the unit into concrete. If it's a rooftop unit, again in northern climates, has to be installed in a way where it's above the snow level. In the southern climates where there is no snow, you do need to make sure these units are tied down to the roof in some way or another. Make sure you check with local building officials and local building code. For maintenance, relatively simple and similar to air conditioning maintenance. Inspect and service the entire system each season before it's used. The customer needs to know how to replace the filters, or there needs to be some filter change program in place. The technician should inspect and clean the entire system, verify proper operation in both heating and cooling modes, measure and record variables such as amperages, voltages, and pressures and temperatures to compare against measurements from previous years. Ask customer about any problems or concerns. Customers live with the equipment. They can tell you about odd noises. Troubleshooting heat pump systems, make sure you listen to customers' complaint. Insufficient heating or cooling, excessive operation, noisy operation. We have a thing with heat pumps called dirty sock syndrome. It's a foul odor. Use a troubleshooting chart to identify possible causes and how to fix problems. Most heat pump manufacturers now put out troubleshooting charts. A common way to eliminate bacteria and mold is to use germicidal ultraviolet lights. However, do not shine ultraviolet lights on plastic drain pans. Ultraviolet lights causes plastic and rubber to deteriorate. It cannot be where there's a drain pan. Place a shade or cover over any plastic parts to prevent UV rays from contacting and damaging plastic parts.